What makes a programming language good or bad? Generally, we need to be able to use it to write programs easily that can be understood and that we can be certain will work correctly. These requirements can be described as readability, writability, and reliability. Readability means that we can easily understand what the program is doing and how it works. Writability means that it's relatively easy to write the program and get it working. Reliability means that we can depend on the program to work as it is supposed to. When we talk about a programming language being readable, do we mean that the computer can read it, or that the human programmer can read it? In truth, both are important, and the characteristics that make it machine readable are very different from what makes a language human readable. Machine readability requires that we have the means to translate it into the computer's own native language. And that requires a translation algorithm that is simple enough to run efficiently on contemporary computers. It is for this reason that we usually use context-free languages, because their grammatical structure is simple enough for easy automated translation, but complex enough to contain the features that we need to write useful programs. Human readability is a very different story. To be human readable, a language must allow a programmer to express algorithms and to define the necessary data structures in a clear way. Efforts to make languages human readable and machine readable can pull a language designer in opposite directions. The result that we get will almost always be a compromise of one sort or another. There are 5 features that make a language readable: simplicity, orthogonality, its control statements, its data types and structures, and lastly, its syntax. To be simple, a programming language needs a small set of basic components. Most programmers tend to learn only those constructs that they need to write the programs that they are working on. As languages get more complex, they develop multiplicity, multiple ways of doing the same type of operations. And this complicates the language and makes it harder to read. This is also true of operator overloading. As operators do more different things, it becomes harder to figure out exactly what they are doing. A great example of multiplicity is adding 1 to a variable in a C language program. There are 2 different assignment statements that you can write, as well as 2 different ways of using the auto-increment operator. And while they look like they mean the same thing, that is not exactly the case, especially if these statements are modified to include another term. Orthogonality means that we can combine a small set of primitive constructs to create the control and data structures of a language, and that whatever possible combinations of primitives that we wish to use are legal and meaningful. It also means that a language feature is independent of where we use it in a language. Non-orthogonalities lead to a large number of exceptions to the rules of a programming language, and that makes it harder to make sense of a program. There are several non-orthogonalities in various programming languages. Pascal functions can only return scalar values. Returning an array requires passing it back as a reference parameter. C and C++ have a similar restriction, which is usually bypassed by returning a pointer to the array. And the only way to pass variables by reference in C requires the explicit use of pointers, which can be a little clumsy and makes programs written in the language less readable. IBM Assembler is not orthogonal because the use of values in both memory and registers requires a different instruction from the case where the operands are both in registers. The VAX instructions are orthogonal because the location of the operand is irrelevant. You still use the same instruction. What makes a computer different from a calculator is its ability to perform different instructions depending on a condition, as well as its ability to repeat an action a predetermined number of times, or as long as some condition is true, or until it becomes true. In the early days of computing, the most common control mechanism was the use of conditional gotos and unconditional gotos. While it was easy to translate into the computer's own language, it had two very big disadvantages. It could be very hard to read and make sense of, and it usually was difficult to write correctly. Later languages introduced features that were much more readable and writable: while and for loops, as well as if-then and if-then-else constructions, which allowed the programmers to write such constructs in a more natural way, as well as making the programs easier to read, which made them easier to check and debug, and subsequently to modify as needed. Originally, the only data types that were available were integers of various sizes, most commonly 8, 16, 32, and 64 bits, and floating point numbers of various sizes. But it became clear very quickly that you needed a way to store character data, and eventually this led to EBCDIC, ASCII, and more recently Unicode, numeric codes that represented printable characters and non-printable or control characters. But that wasn't the whole story. Eventually, programmers wanted to work with data that was structured, and that led to arrays and structures, which are also called records. And they came to the conclusion that using integers or even individual bits to store logical or Boolean values was not that good an idea, because these variables that were supposed to hold Boolean values were actually another type that could be misused very easily. And this led to Boolean data types popping up in programming languages. It became clear that these additional types, as well as the ability to create arrays, structures, and to allow these aggregate types to include aggregate data items such as arrays of structures or structures containing arrays, made it easier to organize data and make programs easier to both read and write. As you can see in the example shown here, it is much better to work with an array of 100 structures than with 4 separate parallel arrays. Storing more complex data structures makes a program more readable and more writable. Syntax is the manner in which we can arrange words and phrases to form sentences, and this applies to programming languages just as it applies to English or other spoken languages. Of course, the syntax of a programming language is much simpler than that of a spoken language. There are features that we can add that will make programming languages easier to read. In older languages such as Fortran, identifiers were limited in length. In the case of Fortran, that limit was only 6 characters, which could make it difficult to give meaningful names to variables. Older C compilers would only look at the first 8 characters, so 2 identifiers that differed in the 9th character or beyond were treated as if they were the same identifier. These days, the restrictions are less restrictive. Current versions of C look at the first 31 characters. Newer languages have either no limits or higher limits, such as 255 characters, making it easier to create meaningful variable names. Unlike some older languages, modern languages require that keywords be reserved. Keywords such as while, do, and for cannot be used as identifiers. It makes programs more readable, because you cannot confuse the variable do with the reserved word do, because do could not be used as an identifier. Form and meaning should go together. This is what orthogonality is all about. But in some languages, this is not always the case. In C, variables declared as static inside a function have their storage allocated when the program is translated, and they may be used or accessed anywhere within that function. And they are only initialized once, when the program starts. Any changes in value remain from one call of the function to the next. But this is already true of external variables, those that are not declared inside a function. The use of the reserved word static limits the availability of external variables to functions within the file where they are declared, which is not necessarily the case for external variables declared without the word static. This difference is significant and underlies a problem. That identical form and identical meaning do not necessarily go hand in hand, which makes a program less readable.